European time, here today on Tuesday, 27th of July. Welcome to our today's edition of Talking Heads from the Security Network Munich. It is my great honor and pleasure to welcome today Rand Hindi from Zama. We just talked before, and so he really, had to move a lot of work aside to open that little window here for us to talk about the future of the internet, not less than this one. And people who had joined our Tech Days security talk a couple weeks ago, Rand was also giving a short introduction to homomorphic encryption then, and I found his talk really so inspirational and visionary that I asked him whether he could be making himself available to extend a little bit that talk from back then, from the Tech Days, to dive a little deeper into this very interesting topic. And gratefully he accepted our invitation, and I'm glad that Rand could make it today. If you have not had a look at his bio, he is, just in short, teaching at Sciences Po in Paris. He is based in France. He was a member of the French Digital Council, and his main focus is artificial intelligence. Rand, welcome. Good to see you. Thank you for joining. So again, he gives this talk, and not much later he will go on vacation. So thank you for the sunny presence from Paris. He, had a very early start into his career already as a child. He was coding and starting his first projects with machine learning and social network development and web programming. So the whole, catalog of internet-related technologies and services. And he was also elected as by the Massachusetts Institute of Technology to be a TR35, and also belong to the list created by Forbes, the 30 most influencing young brains, I would say, under 30. So thank you again for your time. I put this title, The Future of Internet, a little bit broader because, of course, we will look at the same time at the history of the internet, and then from there to the present and to the future. If you look at the website of Zama, so Rand created and founded a company called Zama, starting with a Z, like for zoo. You see that Zama is an open source framework for securing AI applications in the cloud. So we have now a couple of topics that would justify different sessions, AI and the cloud security and framework and open source. So all these things combined in this one here, and so I'm glad that we can learn a little bit more on how this all will interplay. Said this, we will record this session once Rand will take over, and I kindly invite you to write your questions into the public chat that we have here, so that we can later address them after the presentation, and then we will go into a Q&A part of our talk here. I think, Rand, anything I missed?
No, I think all good.
We're all good. Then I'll open the floor. Thank you for accepting this invitation, and I will disappear now and come back when you concluded your presentation. Thank you. And
thank you.
I will start also someone started the recording already. Very good. So we are live and recording, and the stage is yours. Thank you.
Thank you. Hi, everyone. My name is Rand. I've actually been a developer since I was 10. Did a PhD in machine learning when I was 21. And I was running a machine learning company that got acquired a couple of years ago. So now I have this new company, Zama, in homomorphic encryption. I also do quite a lot of angel investing and teaching here in France. But what I want to talk today about is why I actually believe that people shouldn't care about privacy. I know it sounds a little bit controversial, but you'll understand why in a bit. Before I get into that, I just want to share a small story with you about why I was interested in privacy in the first place. When I was 14 years old in the 90s, I started a social network with a friend. This social network grew quite popular. We had quite a lot of people in France, and it had all the features that you could expect from a social network, everything from profiles to pictures to a private messaging feature. So you could basically send private messages to other members. At some point when I was in high school, I actually started getting bullied. So, some random dude decided that, he wanted to beat me up. And not really knowing what to do, I actually realized that he was a member of my social network. And so I went into his private messages, started digging some dirt about him, and went back to him and started blackmailing him, saying that if he didn't leave me alone, I would essentially tell everybody, his dirty secrets. It did work. He did leave me alone, but I couldn't help thinking that what I did was wrong. And even though I had, some kind of reason to fight back, the way I did it was fundamentally wrong. Just because I was operating that website doesn't mean that I had a right to his personal life. No matter what the guy did, I didn't have the right to look at his messages. And so from that day, for me, privacy obviously became something I cared a lot about. It was like, well, if I can do that, then what can all these other companies do with all the data that are collecting about us? And so privacy has been something that's been central to everything I've been doing so far. So when you look back at the history of the internet, in the early days of the internet, when you connected to a website, you were doing this through HTTP, right? It's basically a way to communicate with servers on the internet. The problem is that nothing was encrypted, which means that anybody who was listening to what was happening online could actually see the data you were sending to those different websites. And this was great for governments who liked surveillance. It was great for hackers who wanted to spy on people. But it wasn't so great for, so at the same time as this was happening, a group of cryptographers, the cypherpunks, started thinking about the future of privacy and fighting against the government who was trying to prevent and ban cryptography from being used in the general public. Cryptography was something that people did in the military. It wasn't really something that you and I could actually use. So the cypherpunks started, explaining that you can't really have backdoors, that, privacy is important for everyone. And many of the people that we know today were cypherpunks. Julian Assange, who started WikiLeaks, was a cypherpunk. Phil Zimmerman, who invented PGP, which you could argue is the ancestor of end-to-end encryption, was a cypherpunk. Even Satoshi Nakamoto, the inventor of Bitcoin, was a cypherpunk. So most of the things that we have today to protect our privacy online, we actually owe to this small group of people, the cypherpunks, who wrote this manifesto in the 90s that basically said that, a digital society needs privacy, and the only way to guarantee privacy is through cryptography, encryption. So encryption is an integral part of the history of the internet. And thanks to the cypherpunk who fought against the governments wanted to ban and forbid encryption, it was possible to start designing a new internet protocol that would secure communication. So basically going from no encryption at all with HTTP to encrypting the transmission of data with HTTPS. So in your browser, when you connect to a website, there's this little lock that basically means that the data you're sending is encrypted. But the problem is that encrypting data in transit isn't enough. What we found out is that, if you, let's say, encrypt data on your phone and send it to a server, well, the server has to decrypt it to actually be able to do something. Let's imagine here you wanted to do like some kind of photo editing. They would re-encrypt it, send it back to you. But what this means in practice is that the websites that you're connecting to actually has the data of all its users, right? So even though nobody on the internet can intercept the data you're sending, the person operating the website still has access to all the data. And governments are quite smart. So they figure, well, if we can't really listen to what people send, maybe we can ask those companies to give us the data directly. This is what Snowden actually revealed. But governments are not the only people interested in data. It turns out that hackers also realized that if they hacked and stole this data, they could blackmail people on a very, very wide scale and very effectively. And so as people started using the internet, as more and more data was centralized by fewer and fewer companies, the number of data breaches exploded. So this isn't a question of preventing surveillance alone, it's also a question of preventing data breaches and hacking. So the reason why we actually still like privacy today is because whenever you connect to an online service, they still need the data for processing. So you're encrypting it when you're sending it, but it's not encrypted during processing. So this is something that we can actually start solving with a new technology called Homomorphic Encryption, FHE for short. The idea of FHE is that you can actually do processing on the data without having to decrypt it in the first place. So let me explain. Going again to the example of the photo editing app. This time, I would encrypt my data on my phone, just as I always did before, send it to the cloud for processing, but instead of decrypting the picture and then doing something with it, the cloud basically keeps it encrypted and directly applies its photo editing algorithm to the encrypted data, producing an encrypted result that it can send back to you and that you can decrypt on your side. So from your perspective as a user, nothing changes. You're sending a picture, you're getting a new picture as a response, but now the data is not just encrypted in transit, it's actually also encrypted during processing. So it's encrypted end to end. And by keeping the data encrypted during processing, you can guarantee that the service provider doesn't actually know what users are doing. All they have is an encrypted database of user data. If someone came and had physical access to the server, if someone had literally like root access on the server, all they would get is encrypted user data because the data was encrypted by the user itself, never by the server. So this is really groundbreaking, right? I mean, this is kind of a revolution because it means you no longer have to worry about the security of the data you're sending to service providers, and you no longer have to worry about the people who are accessing the server knowing what you've been doing. You can use this in facial recognition, for example. You could authenticate yourself against an encrypted database of passports. So whoever does, the facial recognition service wouldn't have to worry about people stealing all the precious biometric data. You could use it for voice assistants. Whenever, you've got Siri or Alexa or Google Home in your house, instead of your voice being sent to the cloud for processing, it would be encrypted, sent encrypted to the cloud. And so even if someone could turn on your microphone, all they would hear is some kind of encrypted noise. Genomics, healthcare in general, we see that today with the pandemic. There is a need to share and analyze medical data, but nobody likes to share their medical data, let alone their DNA. But if you can share an encrypted version of your DNA, wouldn't you actually want to participate in all those studies? You could do that. You could literally share your DNA encrypted. People could use it for research. They could use it for diagnosis, even though they don't know what's inside your DNA. I know this sounds really like black magic, but it's really, really important because as this technology matures, as it becomes more and more ubiquitous, it becomes possible to imagine a new internet protocol that goes beyond encrypting data that is transmitted and keeps data encrypted end to end, maybe an HTTP/Z protocol. And at that point, privacy wouldn't matter anymore, not because it's not important, but because your data would be encrypted all the time. And so there is nothing to worry about. Privacy won't be a problem. It won't be something you have to care about because it won't be a problem in the first place. So the reason why I'm talking about this and the reason why, I decided to build a new company tackling that problem of, homomorphic encryption is because as a kid, I was always told the future would look something like that. That, we had to accept that the future was technologically heavy, that we were going to be targeted 24/7, that there was going to be policing and surveillance, that effectively, we had lost control of our lives over a few people who wanted to manipulate us. But with homomorphic encryption, if we can build this new HTTPS internet protocol, it doesn't have to be like that. It turns out that we can actually start feeling safe about using digital services. We can feel safe about having connected devices ever in our home. We can feel safe about using AI for medical diagnosis. And in the end, instead of feeling this oppression of surveillance and targeting, maybe things will be a lot smoother. Maybe we'll feel a lot more relaxed because we'll be able to not worry every day about what happens to our data, exactly as if you were on a deserted island, completely disconnected from the internet. Thank you. Any questions?
Thank you, Rand. Wonderful for this brief, presentation of the concept. I mean, as you said, it sounds magic, almost spooky to imagine how the processing over encrypted data can work. So how can anyone does anything meaningful with data that is encrypted? Maybe you could explain a little bit what methodology or what tooling is behind that option.
So homomorphic encryption is not something new. It's something people have been working on since the 70s. It's just that it never worked because it was either too limited or too slow. It's only in the last couple of years that the technology got to a point where we can actually start using it in real use cases. So that's the reason why we're talking about it today, because it has graduated from good idea in theory to usable technology. It's still very early though. I think we still need a few years, let's say 3 to 5 years, before this can be used everywhere online. But we can already use it for AI today. We can use it for very sensitive use cases already today. So the way that this works is really simple. Homomorphic encryption, homomorphisms in mathematics means same structure. So in practice, what you do is you don't actually change the structure of the data, you only change the interpretation of it. So the encryption and decryption is as if you were translating the data into a language that nobody can understand unless they have the secret key. But the structure of the language itself is exactly the same. So if you do additions, it's going to add the encrypted data together. If you do multiplication, it's going to multiply the additional data together. You won't understand what you're producing because the language is completely, random. But as soon as you translate it back into, something you understand, the result is the same.
Okay, so this is coming to life. I understand from the theoretical modeling, as mathematicians will have, investigated, as you said, since the 70s. Now into coming into practical domains. So does it require? Does it require a specific computational power or AI algorithms to make it practicable, or what would be the precondition in getting it really onto the street?
So by the way, I see people are asking some questions. Yeah, would it be okay if you ask questions directly? I think it's more friendly if people ask them directly rather than.
Oh, okay. I will invite. Yeah. So people, the audience.
If you just unmute yourself and ask your questions directly.
Exactly. Yeah. That will be maybe nicer. So maybe. Hubert Jäger, if you want to unmute and just ask your exactly. Thank you.
Yeah, this is Hubert speaking. Hi, Rand. Hi, Peter. My question is actually on the quantities of the performance. I believe the second question from Kai is the same. In the past, we heard about homomorphic encryption, and we were told it's it needs 10 to the 16 or 10 to even more processing power, and therefore is hard to compare to practical applications.
Yes, so you're absolutely correct. Up until a couple of years ago, homomorphic encryption was more or less 1 million times slower than doing the same thing without encryption. And if you wanted to go faster, you were limited to very basic operations, right? So if you wanted to have a general purpose homomorphic encryption scheme, you couldn't do it fast. If you wanted something very specific, you could do it fast, but you couldn't do whatever you wanted with it. This is now different. Things has changed. The slowdown factor is about 10,000x right now. So still a lot, but it's 100x faster than it was a couple of years ago. And what we are seeing at Zama is that by moving on to things like GPUs, FPGAs, and more dedicated hardware, we can basically start having another 10 to 100x improvements. So by 2025, we're very confident that the slowdown will be less than 10x.
Yeah. Okay.
I heard that in the past it was 10 to the 16th. Now you said it was recently 10 to the 10th.
10 to the 16th was 10 years ago.
10 years. Okay.
10 years ago. I think things have progressed quite dramatically. And we have at Zama today, we basically have the largest research team specialized in homomorphic encryption. Nobody really had a reason to hire that many people to work on that. We do, because we have something that works. My co-founder, in fact, called Pascal Payet, maybe you heard about him if you looked at homomorphic encryption. He invented some of the early techniques in the 90s. We have a very exceptional team that's been able to crack some very hard problems. I would say that today, there is kind of a Moore's law that we can see in homomorphic encryption. We're basically getting a factor 10 speed up every couple of years or so.
Interesting.
Okay,
Yeah.
we have more questions. I would like to ask Dimitris now to ask your question if you want to ask it directly. Thank you.
Yes, thank you. Thank you, Peter. Thank you, Rand, for the nice introduction. One question regarding the kind of algorithms that are, let's say, more suitable for homomorphic encryption. To my understanding, currently not everything is efficiently supported by homomorphic encryption. I understand, of course, that when we talk about fully homomorphic encryption, it means that essentially we can support all sorts of computations. But in practice, let's say, what is the kind of use cases or algorithms that seem to fit a little bit better at this point in time for homomorphic computations?
Quite frankly, there is no longer a limitation to fully homomorphic encryption is fast enough that you can do a lot of things. What we decided to focus on at Zama is machine learning and data science. So for example, you could do, deep learning using homomorphic encryption. You could do analytics, so you could do all that kind of stuff. I think what is still, I would say, 2025 is things like encrypted database queries, like encrypted SQL queries, things like that. I think that will require a level of performance that we haven't reached yet, but we can do it in practice. At least for data science and machine learning, it's not solved, but pretty much there. It's just a question of getting like a 10x speed up from that point. So I think one of the things we've been working on, for example, is providing higher level development frameworks that would enable people to convert their existing code into homomorphic programs. So I can share with you, for example, something that we've been working on. I'm giving you a preview of something secret. But we've basically been working on a homomorphic NumPy framework. So if you guys have done data science, you're probably familiar with NumPy. NumPy is what pretty much everybody uses down, below their frameworks. If you wanted to do a neural network homomorphically, the only thing you need to do is write a code to train it that doesn't change, right? Write your inference function. So you write it in Python, okay? And all you gotta do is call this function called compile FHE. You pass it the inference function that you wrote in plain text that you have here, some parameters on what the data looks like, and that's it, and you're done. So there is nothing you need to know about cryptography to start doing homomorphic machine learning today. This is not a problem anymore. However, the performances might not be what you want because there's a limitation in terms of the precision of the data. There's a limitation in terms of how fast things can go, but there is no longer a limitation in terms of what you can actually do. You could do a 100-layer deep residual network. You could do an LSTM language network. You could do pretty much anything you want. So this homomorphic NumPy is something we're currently testing in private beta. So if you guys are interested, I can put you on that as well. We're expecting to release that publicly in the next few months. So this is where we are with FHE, by the way, right? We're at the point where what matters are the developer tools.
May I also ask something complementary to that? Sorry for taking the time.
Of course.
How do you so let's say that I'm encrypting my data, sending it to some third-party computation party, and they return back the result. How can I be sure, or how can I verify that they haven't, let's say, manipulated somehow the computations, and what I'm getting is not really the correct result, is a kind of manipulated result? So is there the notion of verification, like in cryptography, integral to homomorphic encryption?
So I think that this is a topic that's not about encryption. That's not about homomorphic encryption. That's a topic that is valid for unencrypted computation too. Anytime you send data to a server, even unencrypted, you also don't know if what they're sending back hasn't been tampered with, right? So verifiability is not something that we work on because that's a different problem to solve. Typically something, that you might be able to do with zero knowledge proofs eventually. But, you would guarantee the verifiability of the computation with homomorphic encryption the same way you would do it with unencrypted computation. Is the same problem to solve.
Thank you. Thank you very much.
But by the way, for what it's worth, I think that if you have homomorphic encryption that guarantees that the data remains secret, on top of which you have something like zero knowledge proofs to guarantee that the computation was done correctly, you start to have something that looks like a public computer that you can trust, which I think would be cool, right? Because it means that any device anywhere on the internet, however untrusted, could become a compute node that you can leverage.
Correct.
Put that blockchain with a coordination financial layer, and you've got an AWS competitor.
Thank you, Rand.
Rand, can you please make a comparison of homomorphic encryption with confidential computing from your point of view, please?
Sure. I think homomorphic encryption is one technique in confidential computing. Alongside, MPC, multi-party computation, private set intersection, differential privacy, federated learning, it really depends on the purpose of what you're trying to do. For example, if you want to train a neural network, the most efficient way to do it today is probably with federated learning. Homomorphic encryption would be way too slow to train a network, even at the performances we have today. However, when it comes to inference, once you want to make prediction with a model, homomorphic encryption is the easiest technology to deploy because you don't need multiple servers to collaborate. It's just a client talking to a server with a layer of encryption on top of it. So I think homomorphic encryption is really the sweet spot whenever there is a client talking to a server and you don't want the additional complexity of having multiple nodes like an MPC or federated learning. But if for performance reason you cannot use homomorphic encryption, then you can basically revert back to other technologies. So I would say that they're complementary. If you're working on a system that requires training and inference, you're probably going to be combining different things at different moments in your pipeline.
Okay. May I ask a second time on the performance? You said at the moment it's 10,000x compared to unencrypted or normal or confidential, SGX technology or the other confidential computing technologies. And you said there's a kind of Moore's law of factor 10 every other year, or a couple of years. You said, you mean 2 years? Does that mean 2 years? A factor of, you said 25, 10 times remaining, or 10x remaining, but that doesn't fit together. Can you be more precise a little bit where you think performance is?
10,000x is what you can expect on a GPU today. It depends on the use case, but let's say a GPU is 1,000x to 10,000x slowdown, right? So I think we can get an order of magnitude in the next couple of years by moving to FPGAs, and another order of magnitude by moving to ASICs. I think the 10x is a lower bound of what you can reasonably expect by 2025. The upper bound might be 100x, or something like that. It's a range. I mean, these things are difficult to predict.
That wouldn't be in improving the method. That would be improving. I just heard the hardware to FPGA and. Yeah,
basically, it is basically a hardware acceleration problem now.
Gotcha.
I mean, there's a lot of crypto stuff that you can do, but I think the cryptography mostly improves the precision of the computation. So how many bits of precision you can guarantee. The hardware improves the latency.
But isn't homomorphic encryption in competition with hardware that is encapsulating the decryption and encryption process? Because if you have a server that is completely hardened, encapsulated so that nobody can spy on the details, you could do the operations in the server internally and then send just the result, let's say an average operation on the age of 1 billion people, and you don't want to disclose the age of every single person, would be done on an enclosed server, or you could, as competition, do it with homomorphic encryption. So it seems to me you're in competition with hardware solutions.
You could think that we are in competition with HSMs and solutions like that. You're right. So I think HSMs are still going to be necessary in many protocols to secure things like the private keys and things like that. Homomorphic encryption is really about securing the computation itself. So I don't think it's like 100% competing. I think HSMs have their value in some use cases. When it comes to securing the computing itself, I think homomorphic encryption is going to be a superior solution for one very simple reason, is that it's much easier to guarantee the security of a software solution than it is to guarantee the security of a hardware solution. And so I think, getting hardware right is very hard. Getting software right is hard, but not as hard as getting hardware right. And that's the advantage of homomorphic encryption. It's a pure software solution with very strong mathematical guarantees. The second big advantage, and I think that this is something you're going to sympathize with, there is no side channel attacks possible in homomorphic encryption, because a private key that's being used to encrypt the data never leaves the user's device. The server doing the computation only uses a public key. And so there is nothing you can infer from the hardware itself in terms of reverse engineering the secret key. Whenever you're using, an HSM, the private key is in the HSM. And so potentially you've got an issue there with side channel attacks. Yes. It's a different security model.
But I mean, if you think about how long it has taken to develop secure encryption methods, we're debating whether AES 256 is better than AES 128. Maybe you remember this, or elliptic curves and so on. So it has taken so long for the mathematicians to agree on the security of the standard encryption methods. And now you're telling us that homomorphic encryption is the way to go. So how do you know there's no flaw in homomorphic encryption?
So, no, you're right. There is always a risk, like every encryption technology. However, homomorphic encryption is based on effectively a hardness assumption called LWE, learning with error, which itself is very similar to what you have in post-quantum encryption schemes that are currently being standardized by NIST. So all of this are lattice-based, basically. So homomorphic encryption, if you can break homomorphic encryption, you can basically break post-quantum cryptography, at least two of the major ones being standardized.
Not to mention that we don't have guarantees either for elliptic curve cryptography or RSA. It's all a presumption that they work. So we still haven't found this. So
homomorphic encryption is as secure as lattice-based crypto is secure currently.
Right.
kindly ask all to the audience when they address with their question Rand, just to give a short name and affiliation, so that Rand gets a little bit, just a question of etiquette and politeness, so that he knows who to talk to, and that would be very nice. Thank you.
Yes, I'm sorry. My name is Markus Rothmeier, and yes, I can turn on the camera very shortly.
If there are more questions, Markus, please go on. Otherwise, we take questions from still coming in. Dimitris, you sent a lot of additional remarks and comments. That is just for us to acknowledge, or do you want to add some question?
No, and actually, yeah, I'm Dimitris from Nokia Bell Labs. No, these are I asked them directly to Rand, but I had another question. Rand, do you believe that? So I understand that you have a lot of faith in hardware solutions, and I'm pretty much on the same line with you. But is it safe to assume, let's say, that unless we don't see really a great mathematical breakthrough, that fully homomorphic encryption will stay at the level of non-real-time applications? Because I understand that even with GPUs, even with great hardware advances, it will be very tough to reach real-time applications, especially as we talk about speeds in the 5G and 6G era. What is your view, let's say?
So I think we did have the breakthroughs already. I think the latest generation of homomorphic schemes, on top of which Zama has been built, are good enough. So I don't think a GPU will be enough for real-time applications, at least not all of them. I think it's going to be enough for many of them, but not all of them. But an ASIC, guaranteed, I think should do the trick. What does an ASIC look like? I don't know. But definitely, having a dedicated FHE processor will bridge that gap. There are even ways to leverage quantum computers to accelerate homomorphic encryption. So if you really want to look at like super long term, I think there are many different options. So I think it's no longer a question of scientific breakthrough. I think it's a question of engineering and iterative improvements at that point, really. I mean, I can't illustrate it better. When we started Zama 18 months ago, a year and a half ago, we basically had a slowdown factor of about, a million X, as I mentioned. We're now down to 10,000X. Nobody 2 years ago even thought this was possible. It was not on anybody's radar, because nobody cared to even try, right? And I think there is something really magic that happens when you put together a team of people passionate about a topic and all trying to solve the same problem. We've got 25 people in the company. 16 of them are PhD cryptographers, right? Some of them are some of the people who invented homomorphic encryption. My co-founder Pascal Payet, Ilaria, who invented TFHE. That's a lot of brain power that has never been working together on that problem. So that's why I'm very confident. Things have been moving faster than I expected.
Okay. I wanted to also advise the audience that the website actually of Zama, it's Zama.ai, offers also a range of scientific papers and also a tutorial homomorphic encryption, all the principles and a little bit of the math behind. If that is an additional resource to what we can today.
Also, I'll share with you just like a link here. We monthly meet up on homomorphic encryption where we talk about those things. So very cool. I'll just share. So for example, the next meetup is going to be end of August. We have Google who's going to be presenting the work they've done on homomorphic encryption. So you can sign up to that if you're interested in like nitty-gritty. It is a very technical meetup, right? It's really meant for engineers, cryptographers. What I'm presenting today is much more high level. This is going to be, if you like the hard math, that's where you're going to find it. Also, if you go to fhe.org, we posted the videos of the previous meetups, and so you can more about that.
Well, that's great. So, most future meetups will be also available via your website, Rand, or
yeah. So we have this website fhe.org where we're posting everything.
Maybe one word with the role of open source. On purpose, choose to take that road by what motivation is the thing behind that?
Right. Yes. So everything we do at Zama is open source and published. And the reason, quite frankly, is that you can't really trust something you can't build yourself, right? And so I think when it comes to cryptography, you want people to trust the implementation of cryptography. You need to show them the code. Because the mathematics might be sound and might be strong. If you don't implement it correctly, there is no good. And most attacks in cryptography are not, mathematical attacks, they're implementation attacks. So for us, open source was not even a question. It's just part of doing cryptography.
Understood. Okay. Since we are running this session in 2 channels, we have viewers in the YouTube channel that are sort of watching the broadcast, but also are passing questions. We have sort of a messenger there who will forward those questions over here. While this is happening, are there any questions from the audience in this group?
Not really a question. Midris here again, but maybe to inform the audience here is something interesting that happened recently, and Rand, I'm pretty sure you know about that. I think just recently some homomorphic encryption schemes were accepted in ISO work package work group. I think is it 4 or 1 for standardization. So this is also very interesting. Something interesting that they happen in homomorphic encryption. So we're moving towards standardization, and that's right. Good.
Yes, you're right. I didn't mention that, but this is a very important point. There are standardization efforts happening around homomorphic encryption, and of course, we're part of it at Zama. They're basically standardized BFV, BGV, right, which is kind of like the old historical, homomorphic scheme. CKKS, which is what Microsoft, for example, has been using, and TFHE, which is what I'm using. So I think, if you stick to those 3 families of technology, there's a standard that's going to emerge at some point. All of them, by the way, are based on the same, lattice-based cryptography. It's just that it's a different kind of higher level stuff, but it's this underlying mathematics.
Are there, that you mentioned now these 3 groups, other drivers of homomorphic encryption that you would like to mention, or who are your, you said the meetup will be also, people from Google. Who else is sort of shaping that field? Who are the most important?
I obviously cannot tell you what I know.
Yeah.
I can only tell you that publicly, a number of companies have published works around homomorphic encryption. For example, Microsoft has done quite a lot of work around homomorphic encryption. They have a very good team. Facebook has hired some people to work on homomorphic encryption. We don't know to what extent, but they did publish a paper recently. Many groups in China as well, Huawei, Alibaba, have been working on that. All of this is public. If you look at the literature, you'll find those companies publishing. Different groups have different reasons for encryption, but I think there's a general consensus that if you can, why not? Because why would you want to bother with data security on your servers? Things being encrypted, and who cares that someone hacks into it, right? I think it's peace of mind for people. Beyond privacy, forget the ethical consideration. Practically speaking, if you're a company and you get hacked, that's going to cost you a lot of money. That's going to make you lose a lot of customers. So why not guarantee that the data stays encrypted? It's encrypted.
A typical driver, of course, as we had mentioned before, is standardization, and the other one is regulation, of getting things more private and more secured. Are there also government agencies consulting, Zama or your team with regard to this perspective?
Yeah, it's difficult, because governments. Well, we're kind of back to the 90s, the sci-fi crypto wars. Encryption is bad. If things are encrypted, you can't catch criminals, terrorists. Okay, great. But then we also Pegasus, right? Turns out it's not just terrorists. It's everybody you want to put under surveillance. So I think, in general, there is, let's say, a very schizophrenic regulatory framework where, with the GDPR, the CPA, HIPAA, that are asking for more privacy, and we have, regulation which are no privacy, borderline privacy. If it's not encrypted, it's or if you're trying to. I would like to see them change is the way that a GDP action. Currently, if data it's considered personal information because the assumption is that the server has the key to decrypt it. The regulation GDPR was not built with end-to-end encryption in mind. But end-to-end encryption changes everything because if the data is never decrypted by the server, if the keys remain with the user, arguably, it doesn't matter where the processing happens. So data localization becomes really irrelevant in that particular case. So I think, if the GDPR would relax its definition such that end-to-end encryption could be done anywhere and not necessarily localized in the same country or region, it would completely change the face of cloud computing. You could use servers in a country where everybody is sleeping. Right, it would be much cheaper to do that. So many things would change. So that's one thing I would hope would happen regulation-wise.
Well, that's a quite an interesting take on forgetting about the geographical fencing and localization aspect. Thank you for that idea. Maybe we can transmit it to our data protection experts also in this group and beyond to the regulation side. Well, it's been a very rich talk. Thank you so much, Rand. I don't see any more hands raised or questions. I think there's a lot to process and there's a lot of information coming over. But Markus will have one more question. Markus, please.
Yes, I'm sorry that I missed the beginning of your talk, but let's assume a database company is interested in homomorphic encryption. I have a client who this is a database company, and I've asked the CEO what do you think of it, and then I researched some things, and I found out that today the functionality homomorphic encryption, as far as database operations is concerned, is extremely limited. Can you comment on that?
Yeah, you're right. I think databases is really not what we're aiming to do right now. I think machine learning, data science, analytics is what's more reasonable to do today. This is what we can get good performance on. For many reasons. I can get into the details, but basically databases are hard for one simple fact, which is that homomorphic encryption will always run in worst time. So all your algorithms, you have to consider them to be running in big O time. And so that's why it's a problem for databases, because it basically means you need to scan the entire database for every query you want to do, which obviously is not very efficient. So these are part of the things, that we are trying to solve in the next few years. But as it is today, the performance of a database query would be equivalent to running every single item in your database.
Thank you.
Thank you, Markus, for this question. And Are there any more questions coming up from our audience? If not, I would like to thank you so much, Rand, for really squeezing this in and giving us that little tour on the upcoming encryption future. I mean, we touched many interesting points. Cloud computing being, of course, as you said, one of the clear trends for the future, and then the question how to protect privacy and the processing of information and data. Well, I am sure that you will have some additional followers now in all these meetups and lecturers who will closely follow your work and the work of your colleagues at Zama. I hope we will stay in touch and also organize some physical meeting once this is possible again. That would be great. And thank you so much now from Munich and from our audience, and great to have you. And it's been a really interesting and exciting session.
Thank you very much for having me. I'll see you guys soon.
Yes, thank you. Have a great vacation. This session was recorded. We will publish it so that if you can, digest it again and